So our next speaker will be Professor Yitong Zhou from South China University of Technology. Her talk is about soft hand wrist exoskeleton for rehabilitation and occupational safety. Please.
Good morning, everyone. I'm Yitong Zhou from South China University of Technology. Today, I'd like to share with you our recent progress on soft hand wrist exoskeletons for rehabilitation and occupational safety. So, wearable exoskeletons have shown great potential from clinical rehabilitation to industrial assistance. But the distal joints of the hand and wrist are the hardest to assist. They require fine, responsive, and adaptive motion while demand accurate shape tracking. So our focus, we solve these challenges by proposing intuitive and stable sensing, designing compact and efficient actuators, and integrating lightweight and comfortable exoskeletons. The clinical demands is massive. In China alone, there are over 17 million stroke patients above 40 years old, with 3 million new cases each year. So we aim to provide a unified framework from sensing to hand wrist rehabilitation, and finally to industrial safety and assistance. We began with reliable sensing. We developed a flexible and stretchable fiber optic sensor based on the waveguide loss principle. This sensor uses a serpentine structured silica fiber embedded in silicon. When stretched, the curvature decreases, increasing light intensity. Compared to its nearest relative, FBG sensors, this sensor does not require gratings or laser interrogator, making it low-cost, compact, and variable. So the system includes a laser diode for laser input and a photoelectric conversion module to convert the output laser to electricity, and the data acquisition card for real-time data processing. And we conducted tensile tests, and it was able to withstand 50% tensile strains with 1% resolution. On the other hand, it is robust to various disturbances, such as hot water, folding, twisting, and compression test, making it suitable for variable robotics. To verify its usability, we conducted aircraft game control based on this wrist recognition with 4 such sensors, and robot control, including grasping, placing using 4 arm ring-shaped sensors, which showed a very fast response for real-time control of this human-machine interfaces. This is the very first demo we developed for hand exoskeleton. So we developed a twisted string actuator-based soft hand exoskeleton for rehabilitation. It is lightweight and compliant, using twisted strings to generate tendon-like motion. By the way, it is a undergraduate project developed in my class. And we embedded 9-axis IMUs for finger joint tracking with tracking error of less than 2.5 degrees, which allows real-time 3D reconstruction of VR rehabilitation and grasp training. So we developed a very simple VR game, so the glove can be controlled to grasp a bottle in VR in real time, which is a very interesting demo for this undergraduate student. So that was the rehabilitation part. Then we extended the same soft actuation concept to industrial assistance and safety. So in high voltage line maintenance, workers face significant fall risks. And there are 5,300 fall accidents in Poland in 2017, and a quarter workspace death was due to fall in the USA in 2019. So existing protection devices only prevent passive falls, and long-term operation, especially long-term climbing the towers, can cause fatigue and grip loss. So we proposed a soft hand exoskeleton to assist grip and climbing stability. It enables cyclic hand grip state lock and unlock for active fall prevention. And we designed a variable structure without affecting natural motion. So the climbing can be high frequency. It is around 1 hertz. It requires much faster actuation rather than the rehabilitation. So we developed a fast actuator based on spring energy storage release system. 2 motors are used for the spring energy storage and release, and the time is comparable to the climbing frequency. And then we tested the system in both lab climbing machine and in real tower climbing field tests. And the exoskeleton showed stable cyclic locking and unlocking with no delay or slippage, providing a reliable grip support during ascending and descending towers. So building on these results, we are now developing an integrated sensing and actuation glove. So this one shows the sensing part. So we integrate heterogeneous light guide flexible sensors that can distinguish stretch, compression, and bending in different finger joints. And this glove can achieve specially multiplexed hand tracking. And it can be further combined with soft actuation for integrated sensing and actuation gloves in the future. So to summarize, we aim to develop soft wearable robotic systems that can sense, actuate, and interact naturally with human beings, bridging the gap between human intention and robotic intelligence. Thank you very much for your attention.
Okay, thank you for talking.